Howdy, Cleveland. All right. Hopefully this is working. And hopefully somebody is watching. No. Okay. So no comments. So I don't have to worry about that at the moment. So you might be wondering, Rob, what are you doing? What I'm doing is someone asked me whether or not we could do events in this room with basically a roaming speaker, in the sense that we have someone with a microphone who can then go out into the audience like so, and give the audience the mic so they can ask the speakers questions. And since I have a PlayStation 3 mic that I never really used, I figured, well, why not? I would give it a shot. So I don't know how the audio is. Still no one in the chat, so I will have to worry about whether or not the audio works when I watch this on the replay to see whether or not I am good to go in that way. I also noticed something else about this room. I found the lighting board. Well, that's a generous description of it. I found the lighting options, and this is the best sort of mix between being able for the audience here to be able to see this screen, and for the audience there to be able to see moi. Essentially, there's really no way to shut off these lights or there's no way to dim these lights, which is what would be most ideal, or at least not a way that I know of anyway. So I think that's pretty much it. So what I'm going to do now is because again, I want to test the sound, and because I tend to walk around when I'm talking, I thought this would be a great way to show off the mic, the loaner mic, as it were. Any speaker, any organization who would like to take advantage of this setup, I highly recommend bringing your own mic. But if not, I've got one that you can use. So I am going to blather on about light for a few 2, 3, 6, 7 slides or so. And so, yeah, okay. Oh, I do have someone watching. Woohoo! Maybe they can tell me how my sound is. Maybe they can also tell me whether or not my screen is shared. Problem with this setup is that it's really a two-person job. In order for me to wander around such as this, I can't really see what's going on with the computer. So if there are any active comments, I probably will not be able to get to them very quickly, or really even see that they're there. Particularly now when I've switched over to the presentation. Actually, I'm going to switch back just real quick to see. All right, no comments. All right. So where we left off last time was we were talking about, this is as far as I can go, without extension cables. Last time we were talking about light. We were talking about the fact that astronomers have to be exceedingly clever when it comes to trying to even study their own subject, because we are limited in the laboratories we can use. We cannot simply just take most astronomical objects, stick them in a terrestrial laboratory, and expect to be able to get any kind of meaningful results without, setting ourselves on fire or, collapsing the world into a black hole. Little details. So we are left with trying to understand these astrophysical objects with the only real tool we have left, and that is light. And so last time I talked about various different ways that light interacts with matter. There are essentially 4 of them. There is emission. Light can be emitted from an object, from matter. There is absorption. Light can be absorbed by matter. Light can transmit through matter, and that is a range, meaning that it goes from completely transparent to matter being completely opaque. most matter, if not all matter is somewhere in the happy medium. Nothing is truly opaque and nothing is truly transparent. There's always going to be some factor in between. And then lastly, there is reflection or scattering or refraction. Essentially, the idea is that light will hit matter and then be redirected into some other direction. And that can either mean that the light is unaffected in terms of its own characteristics, or that light gets changed by some fraction. Its energy drops, for example. Speaking of characteristics of light, one of the major characteristics that hopefully everyone is aware of is that the speed of light is finite. Even though it may appear as if when you hit the light switch, the lights immediately turn on, or at least you don't see any kind of warming up phase usually with lights. Lights tend to be appear to us to be instantaneous. That is because the speed at which light travels relative to the typical distances that we encounter on the Earth is very fast. It's around 300,000 kilometers per second. So really, really, really fast. However, space is big, really, 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 really big. And so when you compare the speed of light to, say, even going to the sun, it takes 8 minutes for sunlight. When it gets emitted off the surface of the sun, it takes 8 minutes traveling at 300,000 kilometers per second to get to us. So if Thanos were to snap his fingers and make the sun go away, we wouldn't know until 8 minutes after the fact. And then we would probably very quickly freak out and freeze to death. Anyway, this is not something that has been known for a short period of time. This is not something that we have determined or discovered fairly recently. Actually, it was fairly well known that speed must have a finite, light must have a finite speed all the way back into the 1800s, where a Danish astronomer by the name of Romer was measuring the periods of the Galilean moon, the periods of the Galilean moons of Jupiter, specifically Io, the shortest period, which is a period of around 3 days or so. And what Romer noticed from repeated observations over the course of multiple months was that during times when the Earth would be approaching Jupiter, the orbital period seemed to be getting shorter. And then as the Earth moved away from Jupiter, the period seemed to be getting longer. And he measured the period by looking at just when Io disappeared behind Jupiter and then reappeared in front of Jupiter and then back behind again. Now the reason, and he correctly surmised that the reason for this was that light must take a certain amount of time for the light emanating off of Io to actually arrive at his telescope where he can measure that arrival time. Basically, at the very moment that Io disappeared behind Jupiter, the light that is transmitted from Io at that very moment, as it travels through space, must take a while before it gets to him. And so if you are moving towards towards Io, you're making that travel distance smaller, therefore that travel time is shorter, and therefore the period appears to be shorter as well. And the opposite is true as when you're moving away from Io. So he was able to basically do some calculations. I was going to say back of the envelope calculations, but that's completely unfair to a gentleman in the 1800s. So he did some rather strenuous calculations back then and actually came up with a speed very, very close, within around 10% or so of what we nominally accept as the speed of light today. So this is not something that was relatively new, like relativity or anything like that. So what is light? Now, this is a question that has been puzzling puzzling physicists, astronomers, pretty much ever since Newton back in the 1700s. Now, Newton got into a little bit of a beef with a guy by the name of Robert Hooke. And while Hooke was, during the times that Hooke wasn't busy being a pirate, he was more notably known for his physical achievements. Specifically, if you've ever taken an introductory physics lab and have dealt with a spring, you may have heard of Hooke's law. Hooke's law basically talks about the restorative force that a spring applies to a mass when you compress it, just how much that force actually operates. But Hooke was also very much like the great minds of his time. He dabbled in a lot of different areas, and he was very much invested in the idea of light. And he believed that light must act like a wave, whereas Newton believed, no, well, in order for light to reflect and refract like I'm seeing, it's got to be corpuscular. Basically, it's got to be a particle. But unfortunately, Newton kind of had a mental break and basically was somewhat discredited in terms of his optics research. The Principia, most everything in the Principia, beautiful. His idea that the light was in fact corpuscular rather than a wave, that really wasn't accepted until Planck came along and basically said that light was quantized. And Einstein came along and said, oh, look, I can make electricity using sunlight. And the only way that, well, the best way that that can be explained is if light is in fact quantized. But I'm getting a little bit ahead of myself. Let us go back to Hooke's way of thinking. Let us talk about light as an electromagnetic wave. What do I mean by an electromagnetic wave? Well, I will hand wave a little bit here and just basically say that light, what you really need to know about light is that light carries energy. That's it. Whether it's a particle, whether it's a wave, whatever form you want to conceptualize light, the main thing is that light carries energy. And light and energy can be broken into or can be thought of as propagations within an electric and magnetic field. And so that's essentially, when we talk about light as a wave, that's what we're talking about. A disturbance which propagates through electric and magnetic fields. Another way that the reason why I'm starting off with thinking about it as a wave rather than a particle is that in terms of everything else we're about to discuss about light, particularly in terms of how much energy it does carry, it's a little easier to conceptualize light as a wave. Now, a wave has a few different characteristics. From the top of this plot, you can see that light has a wavelength and an amplitude. Basically, it has a width and a height, or height. The width is, you can define the width any kind of ways that you want. Typically, you'll see it defined as the distance from one peak of the wave to the second peak of the wave, like ocean waves. So they go up, they go down, they go up, they go down, la 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 la. So a wavelength is a distance between a peak to a peak, although you can equally measure that wavelength from trough to trough, so long as you're comparing two comparable points. That is the wavelength. The amplitude you can think of as the height, you can think of it as the intensity. Basically, how bright is the light? And now that I've said that, you can pretty much just ignore that because we are never coming back to amplitude, at least not in this lecture series. Then you have frequency. Oh, I should, before I go to the frequency, I should mention, as I've said before, light has a velocity. Waves, generally speaking, have velocity, whether they be sound waves, light waves, what have you. All waves have a certain speed at which they propagate through a medium. And by medium, what I mean is the substance on which through it travels. So air is a medium. Water is a medium. Believe it or not, that pillar is a medium for radio light. You can't see that pillar because the pillar is behind the camera. So yeah, Believe me, there's a pillar over there, and it is also a medium, or can be. Vacuum can be a medium, meaning the absence of anything can also be technically considered a medium. It is just simply the environment through which something moves through. That is a medium. So, with the velocity, in terms of velocity, now that we know that the waves have a certain velocity, and light specifically has a very set velocity or speed limit, we can talk about things like frequency and period. Imagine, for example, you are sitting on the wave where it says amplitude. And imagine that wave is moving. So right now you're sitting on a peak. As it goes to, say, the right, the wave will drop off into a trough and then rise up back up to a peak again, and so forth and so on. The rate at which it does so is related to the frequency. The frequency is how many wavelengths pass by a particular point in a particular moment of time. And so typically you'll see frequencies expressed like hertz or wavelengths per second. So 60 hertz, for example, is 60 oscillations per second. 60 oscillations of the wave. Complete oscillations of the wave. Period is 1 over that. A period is how long does it take for a single oscillation to move through that particular point in space. So if it's 60 hertz per second, the period of that wave is 1 over 60. Now that I've told you that, you can completely put that out of your mind, because we will never be going back to period again in this lecture series. So the two things you want to know, or the two things you want to keep in your mind whenever we talk about, astronomy, is wavelength and frequency. Those two things are of vital importance. Such that they are in such vital importance, and this is the thing one of the things I love about astronomy. Well, one of the things I love about astronomy and physics is some of the most beautiful, elegant equations you will ever find. 3 variables long. E equals mc squared. F equals ma. C equals lambda f. Or that the speed of light is equal to the product of the wavelength times the frequency. So if you can figure out what the wavelength, if you can measure the wavelength of light by some means, you know its speed, that's been very well measured. You can determine its frequency. And that becomes very important when you talk about energy, or where is that light coming from in terms of this big, beautiful spectrum we like to call the electromagnetic spectrum, or EM spectrum for short. The part of the spectrum that you can see, the part of the spectrum that allows you to see me up here blathering on about light, that is the visible range, or what we call the visible range, hopefully for obvious reasons. But it is a very small fraction of a much, much larger, dare I say, infinitely large spectrum. And that spectrum has 7 major regions, depending on how you want to quantify things. When you're talking about high energy light, high energy photons, or high energy waves, you're talking about gamma rays. Now, unfortunately, or maybe fortunately, gamma rays really don't have a habit of turning into a large raging rage monster. They have a habit of making you dead. So avoid gamma rays whenever you possibly can. And honestly, you might need to question your life choices if that is actually something you need to worry about. Going down the energy spectrum is X-rays. And then lower energy to that is ultraviolet. X-rays we are more familiar with in terms of X-raying our bones and being able to see them. And you might think to yourself, Rob, that seems pretty dangerous. You need to have lead shielding around. And that is true. That is true. The people who administer the X-rays, they leave the room whenever the X-ray machine goes off. But that's a simple matter of how much exposure. Getting a single X-ray is not dangerous. Being in a room where X-rays go off every half hour for 8 hours for 5 days a week or 40 hours a week, that can add up. So that's why those precautions are taken. So X-rays are pretty high energy. Then you get into ultraviolet. Ultraviolet energy we're familiar with because of tanning. If you can get a tan, the reason why you're tan is because of the ultraviolet affecting the melatonin in your skin, causing your skin to get darker. Now, obviously, we're probably all familiar with sunburns. Sunburns is basically when that goes a little too far and you actually cause damage to your skin by receiving too many ultraviolet rays or ultraviolet light. Again, ultraviolet is fairly high energy stuff, and so it can do damage. Now, you might be wondering why we aren't all dead or raging green Hulk monsters. It's because the atmosphere is very kind to us. Or probably a better way of stating that is we've evolved into what we are because the atmosphere has been kind to us. The atmosphere is almost completely opaque, like 99.9 above % opaque to gamma rays and X-rays. It is almost completely opaque to ultraviolet, except for the shortest wavelengths of ultraviolet A and B. Once you get into the visible range of the spectrum, probably why it's the visible range of the spectrum, the atmosphere becomes completely transparent, or pretty close. Almost all of the light from the sun is able to go through the atmosphere, assuming that there are clouds or planes or UFOs in the way, and it will come down and it will strike the earth and it will illuminate your eyes, or you can register it in your eyes. Sorry, lost my train of thought there for a second. One of the things that Newton found, which I may have mentioned before, was that one of the things Newton did was that Newton was able to take white light, or what he believed to be white light coming from the sun, pass it through a piece of glass, which we now refer to as a prism. Particularly if any of you are Pink Floyd fans, you've all seen one. They're on the cover of Dark Side. You take white light, you pass it through a prism, and that because of a thing called refraction, the light gets split into its component parts, at least roughly. And we see a rainbow pattern of color from blue at the high end to red at the low end, or if you flip it, Roy G. Biv. So blue light is higher energy light than red light. Also, an interesting note about Newton. Like I said, a little unstable. One of the stories, maybe apocryphal, but I like it anyway, is that this guy is so dedicated to his field that he was like, all right, the eye has a lens. I know that depending on how the lens is curved, that's going to affect how I see things, or how light travels through it, and ultimately how I see things. Some of you may know, and I'm talking to an empty room, some of you who watch this later on may know where I'm going with this. Yes, as the story goes, he stuck a pin in his own eye and bent his own lens in order to really see, I guess in his mind, what refraction was all about, whether or not he could make a prismatic effect. Now, I don't remember what exactly the outcome of that was, other than ow, but presumably he kept going with it, so I guess it was a success. Now, the 7 regions, keep going with that's right, I'm not quite done with the EM spectrum. So we have the visible range. This is basically all of the light that we can see, which is really just a tiny fraction. If you were to look at the width of gamma rays, the width of X-rays, the width of ultraviolet, visible is much, much thinner in its regime. And it's really the only one that has definitive limits based on biology. And we basically set the blue end of the visible light spectrum to the average wavelength that the human eye can see in the blue end, and the opposite side for the red end. The next one down is ultraviolet. The next one down is infrared. Infrared is heat energy. We think of that as colloquially as heat. When we heat vision goggles are basically a colloquial way of saying infrared goggles. we are all glowing bodies, but we don't see it because our eyes are not attuned to the infrared. If our eyes were tuned so that we could see, instead of 700 nanometer light, we can see 17,000 nanometer light, or 1700 nanometer light, then we would be able to actually see human beings glowing in the dark. We glow, we emit light in the infrared part of the spectrum, not in the visible range. And that is tied to our temperature, and that is a very important factor when we start talking about how is it that astronomers know that the sun has a surface temperature of 5,880 Kelvin. How is it that we know that? A couple different ways, but it is tied to the color that we perceive from the sun. So you get infrared, which is heat, and then next you've got microwave, and then the biggest region is radio. And radio can be broken up into FM, AM, TV, yada yada, 5G, yada yada. So those are your major ranges. Going from high to low energy, gamma, X-ray, ultraviolet, visible, infrared. I've completely infrared, and then radio, microwave, and then radio. Wow. I was hoping that would be much more impressive. Oh well. All right, and with that, I think, with that impressive finish, I think I will finish. So we'll, next time I do this, I will talk about light as a particle. Speaking of which, one of the things that I've been struggling with is really finding my stride when it comes to this channel. And so the thing that I've decided to do is I am going to live stream every Saturday morning, kind of like a Saturday morning cartoon sort of thing. And what I'm going to do is I'm going to give, I'm going to alternate in a certain way. I won't say back and forth because I don't know. The base is going to be a lecture. I'm going to provide lectures on introductory astronomy, pretty much from now until I get to the end of the introductory astronomy textbook that I will be basically using as a framework for this. So we'll talk about light, we'll talk about telescopes, we'll talk about the night sky, Earth, Moon, Jupiter, Saturn, Andromeda, Coma Cluster, dark matter, dark energy, black holes, yada yada. Pretty much anything dealing with astronomy, I will touch on at least in some way. And so I don't know how long it's going to take me to do that. I probably will only lecture for maybe an hour, maybe longer. I don't know. We'll see. But I do plan to do it regularly every Saturday at 10 p.m. Excuse me, scratch that, reverse it. 10 a.m. Eastern Standard Time. So again, I plan on live streaming a lecture every Saturday at 10 a.m. Eastern Standard Time, assuming I got my schedule right. If I got my schedule wrong, then I'll let you all know and reschedule. The other thing that I would like to do is on off weeks, preferably alternating week on, week off, is to actually have interviews with science educators, or actually just educators, really. Doesn't need to be science per se, but just educators. What I really would like to be able to talk about is, particularly in this day and age of not just science denial, but expert denial, of this idea that being an expert in something means that you no longer can be trusted with speaking truth. So I want to talk with educators on how that has affected them, or have they seen that in their work? What is their perspective on the scope of things in terms of society, and what strategies they would implement in terms of combating this denialism. And I'd like it to be international. I'd like to speak with folks from essentially all walks of education. I teach at the collegiate level, but I would love to hear from those who teach at primary, secondary level, or I guess that's pretty much it in the States anyway. At pretty much any level, I'm looking for anyone who is willing to chatter on with me about education, pedagogy, and things of that, and the nature of the world, teaching at any level, and again, really in any field. The idea would be to my focus obviously is science, because I'm seeing a lot of science denialism, but I think it really translates just to expert denialism, that, you know, for some reason or for some way, I think this has been slowly growing over time. There's just been a certain population that just feels that the experts are lying to them, are trying to manipulate them in some way. And in some cases, they may actually have a point. So I would like to have an open discussion about that with educators. All right, well, I'm going to go over to the laptop, and I'm going to see whether or not I have any comments. Step on the cord. Okay, so, Priolti is in the house. Hey, Pri. Hopefully the sound is good. Hopefully the video is good. Hopefully the presentation is good. Good. So, yes. So I'm here reading that, yes, the AV side of things was good. Thank you. Thank you very much. All right. Excellent. Well, then I label this a success. Dun, dun, dun. And with that, I should probably have stopped avoiding doing other parts of my job and actually get to that. So thank you for those who've watched, and thank you everyone who has who will watch in the future. Your interest is amazing to me, so I hope to be able to satisfy any questions or any interest that you might have. And as much as I hate to say it, just to grow the channel or whatever, like, share, subscribe, yada, yada. So, all right, take it easy.